Hello everyone, my name is Mohammad Tariqul Islam. I am first year PhD student at Faculty of Electrical and Computer Engineering, FAC, Unicam. The topics I have selected for this seminar is edge computing, or more specifically multi-access edge computing, or MEC. Uh, at the beginning of this presentation, I will give a brief discussion on edge computing, later on multi-access edge computing and their potential use cases, and later I will cover the two selected paper. So let's discuss about what is edge computing. So edge computing is the application of cloud architecture principles to compute, storage, and networking infrastructure close to the user at the edge of network. Edge computing is typically located at the access point, which is one hop away from the user. For 4G and upcoming 5G network, the access point is and will be incorporated with radio access network or RAN. For 5G and upcoming networking, the edge computing is considered one of the cutting-edge technology. Edge computing provides few features that cloud computing are not able to provide. They are ultra low latency, proximity or closeness to the users, high bandwidth, real-time access to the access network and context informations, security and isolations, and location awareness. Now let's discuss about what is multi-access edge computing. The European Telecommunication Standards Institute (ETSI) promotes multi-access edge computing, or MAC, which was previously known as Mobile Edge Computing Standard, to implement edge computing concept. So they define MAC as IT service environment and cloud computing capabilities at the edge of mobile network within the radio access network or RAN in the close proximity to mobile subscribers. The presence of MAC at edge of operators network enables a large number of new features to be developed in the mobile industry. In order to develop the proper architecture and APIs for MAC, a number of use cases are described in order to derive a consistent set of requirements, listing the capabilities that the mobile edge system needs to support to enable the feature by ETSI. Three main categories have been identified for use cases. Requirements on the architecture are generally quite similar for use cases within a category and quite different between the categories. However, all these categories need to be supported to allow MAC to enable a new era of service within the operator's network. The potential use cases in three categories are network performance and queue improvement services, such as network performance optimization by network traffic monitoring, content or DNS caching, and video optimization. These services are generally aimed at improving the performance of network either via application-specific or generic improvements. The second category is consumer-oriented service. They are gaming, remote desktop applications, AR or VR, cognitive assistance, and so on. These are innovative services that generally benefit directly the end user, more specifically the user using the user equipment. And the third category is operator and third-party services such as big data, IoT, connected vehicles, security, and safety. These are innovative services that take advantage of computing and storage facilities close to the edge of the operator network. These services are usually not directly benefited the end user, but can be operated in conjunction with third-party service companies. For a 5G and advanced network, it is considered that the upcoming network will be equipped with network slicing to serve different particles at the same time, where MAC will guarantee low latency computing resources with a high degree of flexibility offered to verticals and network providers. According to the 5G public-private partnerships, the MAC has impact on different vertical industries. They are Internet of Vehicles or automotives, smart cities, media, e-healthcare, and manufacturing industries. So for this work or for this seminar work, I will only focus on media. So in the area of media or multimedia, there are two applications or services are considered. They are video streaming and AR or VR. Though AR and VR is considered the most rising application for the upcoming networks, but for this seminar I will focus on only video streaming. So according to the Global Phenomena Report, till the year of 2020, 65% of downstream video traffic accounted overall on the internet, which are mainly derived from the streaming services such as YouTube, Netflix, etc. By the year of 2020, according to the Cisco, internet video will represent 82% of the all internet traffic. So the essence of the all the report present that the predominance of video traffic for the foreseeable future. OTT platforms such as YouTube, Netflix, HBO, they adopt dynamic adaptive streaming over HTTP or dash de facto standard for video on demand services to deliver the video traffic to the users. The purpose of the dynamic adaptive streaming over HTTP or dash standard to provide smooth streaming service by adapting network conditions. So how Dash works? Dash works by breaking the video content into the sequence of small segments where each segment contains short interval between 2 to 10 seconds, and each segment is encoded with different bit rates and resolutions, where the server hosts each encoded segments with a corresponding MPD file. On the other hand, the client-side player, such as YouTube players, adaptive bitrate algorithms are responsible to select the appropriate segment from the dash server based on the current network conditions. So, in the context of ETSI-MEC use cases, to increase the overall quality of experience or QoE for dash video service, until now, the work has been done in the scope of content caching, traffic monitoring, and QoE assessment and bitrate optimization. So in the literature, there are several work proposed for efficient way of content caching at the edge of the operator network. Also, there are a few works which shows the efficient way of traffic monitoring and QoE measurement at the edge of the network. The reason for select the edge point for traffic monitoring that the video traffic is considered at edge point less mixed with cross traffic interference than other part of the network such as core network. And lastly, the several work has been done to propose the MEC assisted approach to select more appropriate bit rate to enhance the overall video quality beyond the client-side adaptive bitrate algorithms. So for this seminar, I have selected two papers which is focused on content caching and traffic monitoring and QoE assessment. So in the upcoming slide, I will tell more about those selected papers. So the first paper I have selected, which title is Machine Learning Driven Dash Content Prefetching in MEC-enabled Mobile Networks. In the previous slide, I discussed about that video streaming traffic is the most dominating traffic these days, and for the upcoming future, the video streaming traffic will take place a significant portion of the total internet. And on the other hand, the cutting-edge technologies such as multi-access edge computing technology will enable the mobile network operators to provide network service at the mobile edge. So the effective handling of video traffic at the edge by the mobile network operator will become very important to satisfy a customer with their intended video quality of service or QoS, as they stream a higher volume of video which at higher qualities. And I also mentioned in the previous slide that the video streaming platforms or OTT platforms such as YouTube, Netflix, they adopt dynamic adaptive streaming over HTTP or DASH standard to deliver video content to the end user, which purpose is to dynamically adapt the network changes and select the best video segment to provide the highest possible quality of experience to the end users. So caching video content closer to the user, specifically at the edge MEC server, can benefit both users and mobile network operators. So it reduces the content access delay for the users, which will improve the end users quality of experience, and it will also decrease or alleviate the bandwidth load at the backhaul part or in the core part of the network. But to cache the video content at the Mac, there is a drawback due to the limited capacity of the Mac server. So for this, there is need a intelligent decision that what type of content we need to cache and where to cache it efficiently or effectively. So for this purpose, in this paper, the author presented a machine learning based predictive prefetching and caching approach for dash supported video streaming, which implemented at the Mac server. And the author used ensemble method for machine learning based video segment request prediction and an integer linear programming technique for content prefetching or caching decisions. So in the paper, the proposed section method, the authors first discuss about the machine learning prediction model. So the prediction algorithms runs periodically over prediction windows to predict the request expected in the next window. So here the request it refers to the video segments, and this prediction is made for each dash client respective Mac server at each decision instant before the integer linear programming is run. For each client, the integer linear programming requires a prediction of the segment request and their bit rates, as well as the prediction of G-node-P association to know which Mac server node in the network to cache the content. So this is the scenario of the prediction algorithms with both input and output, where the prediction window size is denoted by the delta t. Here this is the prediction window size delta t, and this line actually means the decision instant. So at any given decision instant k, the radio access network and dash client related metrics are collected over the matrix aggregation window, which later will be used as input for the machine learning model. The three kind of machine learning model. They are number of segment predictor, mode predictor, and or bitrate predictor, and G-node-P predictor. So since the integer linear programming runs synchronously, the prediction output P for each client and at the decision instant k must include the number of segment expected to be requested by the each client over the prediction window, and then the expected bit rates of these segments, and the expected G-node-P association to place the content. And here I mentioned that there are the three type of the author used three type of machine learning model, where the first model, the number of segment, will returns the expected number of segment requested by the client. The second model, mode or bitrate predictor, returns the most frequent bitrate of the request segment for client N. And third one, G-node-P, the G-node-P predictor returns the expected G-node-P association for client N. So the G-node-P association is relevant when considering the client mobility, since it determines where to place the prefetched content. So incorrectly or wrongly allocating Mac capacity to the content will negatively affect the cache hit ratio. So in the next slide, I will more tell about elaborately what is cache hit ratio. So each predictor or the machine learning based prediction model is designed as a multi-class classification model where the first two type of predictor, number of segments and mood predictor, that depends on the choice of delta t, and the third one, G-node B predictor, depends on the number of MEC edge server. The input matrix used to train the number of segment and mood predictor either directly or indirectly influenced by the bitrate chosen by the client-side adaptive bitrate algorithms, and the input matrix used to the G-node B predictor influence the client's G-node B associations. So both type of input matrix can be obtained at the MEC server through the radio network information service and a monitoring component that logs the current state of each dash client based on the segment request and responses that pass through the MEC. So after explaining the machine learning model, the author discuss about the integer linear programming model. First they stated the problem statement where they consider a mobile network which is composed of the user equipment's 5G core, 5G G-node B base station with a MEC server co-located with the G-node B, and the MEC server are characterized by the processing memory and storage resources. The authors consider that at any given time a set of requests will be issued from the user equipment for a set of video segments, possibly in different bit rates, where the machine learning model that I explained in the previous slide is responsible for predicting the segment request and the bit rate and the G-node B associations of each user equipment. So after obtaining the prediction results from the machine learning model, the integer linear programming model will take decision whether to prefetch the request video segment in a specific bitrate to the network edge, or if available to transcode higher bitrate segments available at the network edge to make sure that the bitrate requirements of the user equipments are satisfied while network resources are used efficiently. The author also consider the 5G network composed, as I said, composed of a MEC server co-located with G-node B and 5G core, which are the interconnected by the transport links, where a set of user equipments that are connected to this G-node B make video segment request with specific bit rates. So author defines their main jobs to find joint video segment prefetching, transcoding and resource allocation solution with the objective to maximize the cache hit ratio and the byte hit ratio. So where the cache hit ratio refers to the number of requests served from the edge to the number of requests issued to the network, and on the other hand the byte hit ratio refers to the number of bytes served from the edge to the number of bytes requested by the user equipments. After defining the problem statement, the author used the undetected graph modeling to represent the mobile network model, where the N represents the set of nodes that can be host video, and where the E represent the set of links connecting the nodes in the graph, and similarly the other parameters such as C CPU that represents the number of CPU cores available on the node, then the C STG is refers to the caching storage of the node, and the CPWT it refers to the bandwidth capacity of the substrate link. Similarly, they use a directed graph to represent a user request model, where the N is the union of user equipment and their request bitrate of a specific video and segment, and the E represents the virtual link between the user equipment and their requested bitrates. And apart from this, the omega beer, it represents the bitrate of the given requested video segment by the user equipments. In the problem formulation section, the authors consider the joint video segment prefacing, transcoding, and the resource allocation problem in a type of a virtual network embedding problem, where virtual network embedding problem embedding is a we know that is a key area in the mobile network virtualization. The purpose of the virtual network embedding is to map virtual network onto an underlying physical network that means as a substrate. Typically, the virtual networks have a certain demands such as resource requirements, and that need to be satisfied by the mapping process. So a virtual network can be described in terms of vertices or nodes and edges or links with certain resource requirements. To embed a virtual network, substrate resources are assigned to these vertices and the edges. So if you want to know more about the virtual network embedding process, so here I am mentioned to paper from where you can get more about know more about the virtual network embedding. So the embedding process is performed in two steps: node embedding and the link embedding. In node embedding, each virtual node in the request is mapped to a substrate node, and on the other hand, the link embedding, each virtual link is mapped to a single substrate path. For the ILP formulation, the authors they used ILP technique as a VNE problem with a two objective function that tends to maximize the cache hit ratio by the given formula, and as well as the maximize the byte hit ratio by the given formula. Since we know the virtual network embedding problem is an NP-hard problem and it requires several constraints to be satisfied. On the other hand, the integer linear programming, which was formulated based on the virtual network embedding. So authors in the paper they mentioned that they have satisfied following constraint for the valid solution. They are number one, they ensure the storage used for storing the videos does not exceed the maximum storage capacity of the edge node. Number two, at the given time, each user equipment should be provided with one video segment in the request bitrate. Number three, ensure the virtual link are mapped on a substrate link as long as the link has sufficient capacity. Similarly, the number four enforce a continuous path established between the user equipment and the bitrate of the video segment in the virtual request. And number five, guarantee video segment is available at the edge only if at least there is one user equipment requesting the video segments. And the number six, ensure the number of CPU core utilized for transcoding are not higher than number of CPU cores available at the edge. Now in the evaluation part for data collection, the author used NS3 network simulator which support dash implementation, and the setup consists of 12 G-Node B and a variable number of user equipments between 27 to 68 that move between this G-Node B with the velocity ranging between 1.4 to 5 meter per second. The monitoring and application level data is collected over 27 runs of 1000 seconds each, where 23 of them were used to training the machine learning predictors, and rest 4 of them were used for evaluation of predicting prefetching for the ILP program or model. And then the user equipment in the network request segments from one of 10 live stream videos. Now for the machine learning based activity, the author use two type of algorithms: random forest and extreme gradient boosting. And then this is the table for the accuracy of a train model, machine learning model using different prediction window and matrix aggregation window size. So from here we see that the number of segment predictor for the number of segment predictor, the extreme gradient boosting got the highest test accuracy, which is 83.3%, using 4-second prediction window size and 4-second matrix matrix aggregation window size. And for the mood predictor, here also the extreme gradient boosting got the highest test accuracy, which is 89.7%, using 4-second prediction window size and 10-second matrix window aggregation size. So here is one interesting insight in the paper. It mentioned that, and also we can from here we show we see that when there is a more prediction window size is more, the overall machine learning based accuracy is less. Now for the another predictor, which is a GNP predictor. Actually in this part the author didn't mention actually which algorithm they use. They just mentioned that due to the smaller number of metrics with a simple relationship to the target prediction, it obtained a test accuracy close to the 100% regardless of the model employed. And the best performing model were used to provide the required input to the integer linear programming. Now next, for the integer linear programming based prefacing, the scenario consists with a MEC server with a different storage. They are 25, 50, 75, 100, 125 and 150 MB. And the prefacing integer linear programming or ILP algorithm runs periodically over 4 seconds, which is also known as prefacing time slot. And the cache at the MEC server uses a simple list recently used or LRU replacement strategy for content management. And the cache hit and byte hit ratios results are averaged over 4 runs, and 95% confidence intervals were obtained. And this is the result for the ILP based prefacing, specifically for the cache hit ratio, byte hit ratio and bandwidth link utilization, where in the we can see the cache hit ratio. The cache hit ratio result was based on different cache size, where a higher cache hit result in the end user experiencing less delay and resulting in obtaining higher bit rates. And the average cache hit ratio for the smaller cache size is higher for the cache hit objective compared to the byte hit objective. And that the discussion from the discussion, and the authors mention in the discussion part, the author mentioned that the ILP cache hit can make the more intelligent content prefacing decision when there is limited cache storage at MEC than the ILP byte hit algorithm. And for the byte hit ratio, with more byte sharp at the edge, more saving over the bandwidth link can be achieved. And the byte hit ratio is the ratio between the number of bytes sharp from the edge and the overall number of byte request. And in the discussion part, the author mentioned that the number of bytes sharp from the edge for the ILP byte hit algorithm is more than ILP cache hit algorithm. And the last figure, or number C figure, is for bandwidth link utilization. So this is compared with the baseline in which all the segments are sharp from the core and no prefacing is performed. And here we can observe that the ILP byte hit achieves the lowest bandwidth link utilization compared with the baseline. So in the conclusion part, in this paper, the author proposed a novel method for the machine learning driven predictive prefacing for problem of dash video streaming in the MEC-enabled mobile networks, where a machine learning model used to predict number of segments, number of segment requests, bitrate and GNP association, and the ILP or integer linear programming based model were used to content prefacing. And they showed with an accuracy of 83, 88, 98% for the 3 predictive tasks, and using the MEC to prefetch segments that gain the cache ratio of 60%, which implies a reduction in access delay for 60% of the request. And moreover, they also demonstrated the bandwidth link utilization could be reduced by the 69% through the caching at the edge using maxed byte hit objective in a live streaming scenario. Now let's move on to the second paper which I have selected to present in this seminar, which title is Real-Time QoE Estimation of Dash-based mobile video applications through edge computing. These days a large number of videos are streamed through different type of device, is mobile phone, tablets, PC, and so where the video contents are delivered to these devices through the RAN. So RAN is a point where the most of the packet errors are frequently occurs. So since we know that Dash standard video depends on the network condition, and due to the instability of radio access network or RAN, end user may experience the poor video quality, such as rebuffering event or quality lower quality name or quality changes frequently. So therefore it is important to assess the end user quality of experience or QoE at a runtime or real-time fashion, and perform any intelligent operation at the edge of the mobile network, which we defined as a MEC, to fix the user quality of experience if there is such any quality of experience degradation occur. So such type of QoE estimation can help network operator to adapt its RAN resource allocation so that client get more radio resource, and also this kind of information can used by the content provider to make any changes in their video adaptation strategy or scheme. So for this, in this paper, the author present a MEC-enabled novel QoE estimation scheme that works robustly in a RAN environment in real time, where packet error frequently occurs, and with a high accuracy and low CPU and RAM footprint. And their proposed scheme is packaged into a virtual network function and deployed in a real LTE network infrastructure, which serve as a use case for the MEC paradigm. So apart from the QoE estimation, their proposed schemes also able to identify different dash sessions from each other, even when network address translation is used and all the dash clients are exposed with the same IP address. And in the background review section, the authors discuss about the dash working approach, which I already discussed in the earlier slides. Each of the video segments would be encoded with the different representations such as bitrate and quality, video quality, where each of the representation will be described into a media presentation description file, where the client first will request for the MPD file, and based on the MPD file informations, and the client side adaptive bitrate algorithms will request each of the segment based on the current network conditions. And in this section, the authors also mention about a different kind of the quality assessment technique, such as a direct client feedback in network QoE estimation, and mapping QoS parameters to QoE in mean opinion score. So for this paper, the author focus on second category, which is consist of real-time in-network QoE estimation technique and offline techniques, and they emphasize on 4 objective QoE metrics. They are the video buffer, the available video buffer at the client. Second one is initial playout delay, the time duration between when a client clicks to play and when the video starts playing at the client. And third one is rebuffering or stalling event, the number the number and the duration of the rebuffering events during a sessions. And the last one is the video quality switching, the number of events where video quality switches between segments. For the system overview, the authors consider the LT network architecture as an example where the MEC is deployed within the mobile network infrastructure between the base station to packet gateway, and the queue estimation is placed at a MEC server as a VNF or virtual network functions. The overall the queue estimation scheme is consist of four functional blocks. The first one is the first block is HTTP proxy, which is responsible for handling incoming dash request, and their proposed scheme support both forward and reverse proxy when the dash session is unencrypted, and if the session is encrypted, the scheme will only work with the reverse proxy to decrypt the TLS connection and TLS connections. And the second block is the packet sniffer, which responsible to capture packet on transport layer and identifies all the dash related ones, and it then process each of the packet information into an efficient one-line format, which include the timestamps, TCP port number, the sequence and acknowledgement number, etc. So for this work, as a packet sniffer, they use TCP dump because the TCP dump tool is takes less memory and more lightweight to capture large amount the packet into the wild is compared to the other tools like as the T-Shark or Wireshark. And third block is queue estimation algorithm, which process the input from the HTTP proxy and the packet sniffer and estimated the mentioned 4 objective QoE metrics earlier, and later it stored the estimated QoE knowledge into the user QoE repository. So where the user QoE repository, as I told, that it is responsible for store all the dash clients current and the historic QoE knowledge, which can be later used by the mobile network operator or the content service provider to perform or to take any concrete action for the QoE driven optimizations. Now let's move on to the queue estimation algorithm. So for any video streaming session, to identify the video quality, first we need to identify the video session start and end correctly. So without identifying video session correctly, it will predict the false quality estimations. So for this, their proposed algorithms identify which dash session a request belongs when HTTP proxy receives a video segment request, and it checks if the packet is dash relevant packets, and if yes, then which dash session does it belongs when the packet sniffer capture a packet. And the algorithm also maintains a list of all dash clients, where each of the clients contains a list of dash video sessions, or they put this term as a VS, where the video session instance is created every time an MPD manifest request is sent from the client. And each video session contains a list of video segment download session or SDS, where an SDS instance is created every time the segment request is sent from the client. So in order to calculate the video quality from the client request, and the algorithm needs to know about the exact URL that contains the segment information. So as I mentioned earlier, that at each dash video streaming session, the client first requests for the MPD file. So when the MPD file is sent from the video source to the client, the HTTP proxy keeps a copy of that file and parses the URL of each representation, each segment, and generates a lookup table. And then every time the client requests a segment, and the proxy is able to map the URL contained in the HTTP GET request into a specific segment ID and representation. So thus it calculates video quality and quality changes event with 100% accuracy on per segment basis. And after evaluating video quality to calculate the video buffer estimation, They also proposed the algorithm which is shown in the right side, which responsible to calculate client buffer status as well as initial playback delay and rebuffering events. And the algorithm is executed periodically over on each video session of each dash client to estimate its current buffer by iterating through its segment download sessions list. So in these algorithms, the line 7 to 14 is responsible to calculate the buffer value. If the buffer result turns out to be the negative, it means the rebuffering has happened. And where the line 15 to 17, it deduct the gap between the current time and the last segment download sessions finish time from the buffer. And the line number 18, it adds the last finished segment download session length to the buffer. And at the line 21 to 25, it updates the video sessions rebuffering statistics if the initial buffer result is negative after iterating through all the segment download sessions in the list. Now for the performance evaluation for the experimental setup purpose, they used user equipment using the PC running over Ubuntu 16 operating system, and the Google Chrome browser, and dash.js as a dash player, and where the user equipment is connected to an LT band 41 small cell via Huawei Nexus 6P mobile phone through USB tethering. And the QoE estimation scheme as a BNF deployed next to the packet gateway in the network mobile network infrastructure, where the HTTP reverse proxy is implemented through the JT TCP dump as tool as used as a packet sniffer, and Java-based program used to implement the QoE estimation algorithm, and MySQL used as a QoE repository. And for the evaluation purpose, the author used three kind of network scenario with a different latency and different packet rate with the same rand condition, and they defined the three condition as a three different name: ideal, fluctuating, and poor network condition. So this is the scenario where the estimation where the algorithm estimated the video buffer. So here the red line indicate the real buffer status, and the blue line indicates the estimated buffer status by the algorithm. So from this figure we can show that the red line and blue line are very close to each other. Thus means that the algorithm, the proposed QoE estimation scheme is able to estimate video buffer with nearly accurately with real-time results. And this is the result or table for the results for the initial delay, playback duration, and rebuffering number and duration. And then we can see that the result for each different three kind of scenarios, A, B, C, that means the three network scenarios where the estimated value is very close to the real value for the three type of for the given metrics: initial delay, playback duration, and rebuffering events. And later, in order to evaluate the QoE estimation scheme, in order to evaluate the proposed QoE estimation schemes, CPU and RAM uses, the author used the same setup with 10 concurrent dash sessions were maintained over 24-hour periods. So in this figure, in the right side indicates the CPU uses, and the left side indicates the RAM uses. So CPU users is maintained at a low level with an average of 0.32%, and for RAM users we can see that at initial it is higher due to the program initialization, and later it get steady with an average of 36.87 MB. So that's it for the conclusion. The author proposed a novel scheme that estimates dash video applications QoE in real time through the edge computing, where the algorithm doesn't rely on capturing any key packet in the dash session, and it is able to ruling out packet errors by the inspecting TCP and IP level header only, which means it works robustly in the RAN environment where packet error frequently occurs, and it is also capable to distinguish video session behind the network address translation. And by real LTE network testbed, they demonstrated that the proposed scheme can predict QoE metrics with a high accuracy and taking lower CPU and RAM uses. And till now, it is the first QoE estimation as a virtual network function that has been packaged and deployed in a real MEC server. So that's it. Thanks for listening. And if you have any questions, please feel free to put in the Google Classroom. I will try to answer them.